Now I'll introduce another vector operation, dot product. The dot product of two vectors is the sum of the product of corresponding elements. So, for example, with vectors represented as lists, u1 through un and v1 through vn, the dot product is the sum of u1 times v1 plus u2 times v2, and so on. Now notice that the output of dot product is a scalar, not a vector. For this reason, dot product is sometimes called scalar product. Here's one use of dot products. Define D to be the set of the four main ingredients of beer. We can define a cost vector that maps each of those ingredients to the cost per unit amount of that ingredient, and a quantity vector that maps each of those ingredients to a quantity. Then the total cost is the dot product of the cost vector with the quantity vector. We could also define a value vector that maps each of the ingredients to, say, the caloric content. And then the total calories represented by a pint of beer is computed as the dot product of these two vectors. A sensor node is a small hardware device that has a bunch of components in it, such as the CPU, radio, some kind of sensor, and some memory. Now, these things are battery driven. This is where you put the batteries, and usually you leave them in remote locations. So utilization of energy is very important. We want to be able to, we want the sensor node to not use much energy. Now, suppose we know for each of these four hardware components how much energy it draws. Okay, we'll represent that as a vector. The domain of the vector will be the labels of the individual hardware components. So here's an example of such a vector. It maps the radio to the amount of current that the radio takes when it's on, the sensor to the amount of current that the sensor takes when it's on, and so on. Let's say we have a test period during which we know how long each hardware component is on. So this might be the vector representing a test period. So the radio was on during the test period for 0.2 seconds, and so on. The total amount of energy consumed during the test period can be expressed as the dot product of the duration vector with the rate vector. Now, it turns out that for these devices, we can't measure the current draw for each of the individual hardware components. We can only measure the total drawn by the sensor node. And we're interested in figuring out how much each component draws. How can we do that? We can't, for example, turn on the memory without turning on the CPU as well. So here's the idea. We run several tests on the sensor node, and in each test, we have an idea of how long each component is on during the test. We measure the total amount of current flow during that test. And now we can set up an equation, a linear equation, for each test period that says that the dot product, the duration vector for that test period with the rate of consumption is some specified amount, the total draw of energy during the test period. Now, this vector rate is actually a vector of variables. And the idea is that by solving this collection of equations, we can figure out what the entries of the rate vector are. That is, how much current is drawn by each of the hardware components. Now, there are questions that come up. Can we use these equations to find numbers for the rate of consumption of the individual hardware components? And supposing we find those equations, is that enough to pin down precisely what those values are? Or is it, in fact, that there might be multiple solutions to this list of equations? The answers to these questions will have to wait a little bit. So more generally, given a set of linear equations like this, called a linear system, how do we know if there's only one solution? And what if our data are slightly inaccurate? Can we nevertheless get a solution that's very close to the true solution? So we'll have to wait on these questions. Here's another use of dot product to measure the similarity of vectors. Well, let's say we look at a period of time in which senators are voting on many, many bills. You could represent each senator's voting record as a vector, where for each bill there's an entry plus one, minus one, or 0, depending on how the senator voted. Say +1 if the senator voted in favor of a bill, -1 if the senator voted against the bill, and 0 if the senator abstained. So we have a vector representing how the senator voted on many bills. Now, we can compare that senator's voting record to another senator's voting record by taking the dot product of those two vectors. For corresponding entries, if both of them are +1, then this contributes a 1 to the dot product. If both of them are -1, this contributes a 1 to the dot product. In either case, that means the senators agreed on that bill. If one of them voted in favor and one voted against, then the product of corresponding elements is -1, and so that takes away from the dot product. Overall, the value of the dot product is high if the two senators agreed a lot, and low or even negative if the senators disagreed a lot. Here's another application. You want to search for a short audio clip within a larger audio segment. Now, audio is some crazy waveform. I've shown it here. A digitized version of audio looks more like this. The audio signal is sampled at regular intervals. So really, a digital representation of an audio segment is a bunch of numbers. Take the sample of the signal at various times. So we can compare, let's say, two equal length audio segments by taking the dot product. At a particular moment, if both of them are positive or both of them are negative, that will contribute positively to the dot product. If one is positive while the other is negative, that will contribute negatively. So the higher the dot product, the greater the similarity between these two audio segments. But now let's get back to the problem of finding a short audio clip within a longer audio segment. We don't know exactly where the audio clip is supposed to appear in the longer segment. But let's say we have some guess as to where it is. So we can take a dot product of the vector representing the short clip with the corresponding subsequence of the long audio segment. And again, the higher the dot product, the greater the similarity between them. Now, ordinarily, we don't know where the short clip appeared in the long segment. That's why we're carrying out this computation. The way to handle that is to take lots of dot products. Think of all the different possible locations for the short audio clip. It might be at the beginning of the segment, slightly in, and so on. Lots and lots of dot products. But perhaps the higher dot products give us clues as to where the best match is. Now, this seems like a lot of dot products to take, but there are shortcuts. In particular, there's an algorithm called the fast Fourier transform that enables you to take all these dot products very efficiently.